Yeah, okay. So this is the sixth tutorial session on NPTEL online course on finite element modeling of welding processes. So today we would be our plan is to review some of the topics that have been discussed throughout lectures 1 to 6, and then we would also be uh, trying. We'll also look at some problems which can be solved in Phoenix, such as time-dependent problems. So we won't be coding anything, but we'll just take a look from various online resources as to how to solve time-dependent problems, because that's what we would be requiring to model some of these heat source models that have been talked about in the past 2 weeks in of the course. So let me just share the notes which has been provided us to by the instructor. So yeah, let's just go through whatever has been covered here. In week 1, we discussed about introduction to welding
No,
processes.
you're not sharing anymore. Something happened.
Okay, okay.
No, not sharing the screen anymore.
Now, now,
No, yeah,
yeah,
now it came. Now it came.
yeah.
Yep.
Yeah, so in the first week, we discussed about the introduction to welding processes, when the different types of modeling approaches and the welding, so to speak. So throughout the course, fusion welding is where the entire focus has been led. So we'll be reviewing just the fusion welding part. Then we look at the advanced welding processes, and we'll only be considering those things which are relevant for the higher weeks. For the later weeks. Then there was talk about the fundamentals of finite element method, and also about how to and the different heat source models which are used for conduction mode welding. So conduction mode welding requires low it's and and there is again about heat source models. Even in week 5 it continues, and week 6 there are certain how to implement FEM to model welding processes. So that's what we are going to review. We'll just give a very fast review and then look at some of the numerical approaches which has to be done. So let me just open the first slide, and
Okay.
so here, so we start with the introduction to welding processes, talk about introduction, classification, fusion welding. So we'll only look at fusion welding because that's what is relevant for our discussion today. And these are some of the material processing technologies, and what are the different types of metals and alloys, and physical properties of materials, high thermal conductivity, metals with low thermal conductance, thermal expansion, then the mechanical properties such as stress, strain, elasticity, plasticity, toughness, resilience, creep, and fatigue and hardness, and microstructural measurement. And about the different types of modeling, one is fixed physics-based modeling approach. The other is so in this case, what we do is there are one way is, and then we also have what we call the phenomenological modeling, in which case we derive certain the parameters for certain relations that we make between, say, stress and strain. And this is known as phenomenological modeling. So phenomenological means we study a phenomenon experimentally and then try to fit certain parameters, fit certain relations between derived quantities and determine the parameters.
I think one example of this could be.
Uh, could you, it's not very audible. Yeah,
Oh,
yeah,
right. Is it okay now?
yeah. It's better. Yes.
What I'm trying to say is, so this phenomenological modeling, I think, let me give it a shot. Say you have some constant model which involves some
Huh.
constant such as heating constant, when it will melt, when it will break. Okay, so
Huh.
you'll have a constant model. I think in this he might use something called Johnson Cook constant model for elastic plastic bodies. Okay, so
Yeah.
while you're
Yeah.
welding now, so
Huh.
there could be like after some heat, suddenly it becomes plastic. So there
Huh.
should be
Huh.
a
Huh.
your stress and strain.
Huh. 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 Huh.
So, so what happens is someone will sit and derive this relation, and you should do experiment and find those constants. and just use them in the model. I think that's what phenomenological modeling is. That's what I understood. But let us see.
Yeah, that's
If,
what it is. Yes.
okay.
Yeah,
Okay.
that's what it
Okay.
is. Yeah, we first do some experiments and then try to devise certain relationship based on that, based on looking at the graph between the quantities that we want to form. I mean, that it has to be related through this constitutive law. And then that we determine those parameters which form that relation. So that is what it is, phenomenological model. And the other is what we call as the physics-based model. So in this case, we use we move from the fundamentals from first principles approach. So it's like the new Hawkian model is considered to be a physics-based model in the physics-based model constitutive relation, because we start with the principle from the principles of statistical mechanics and then build the theory till there. So we see that they are related to related from a very much an atomistic picture. Yeah. Okay, and then there are something this all these multi-scale models. So there are different levels of studying a problem, right? Say based on some length scale. Say in this case, the axis gives us in terms of angstroms. So electron. So if it happens to be of the order of 1 angstrom, then we have to do something called electronic structure or ab initio. Then we have at higher levels, we have atomistic models, and then microstructure FEM based models, and then continuum CFD slash computational engineering based approaches.
I don't know why
Then
he wrote
we
microstructure as FEM and continuum as CFD, because FEM can also do continuum.
yeah, that's no, that's why he says C, right? So C, yeah, something like computational
But
engineering. I don't.
FEM also assumes it to be continuum, no? If I'm not wrong.
Yeah, that's what. So it's like yeah, they have done some not
We'll
properly
see.
given from where, yeah.
Yeah.
And then why there's importance of multi-scale modeling, it depends on where we look at what problems we are solving, isn't it? So that's what continuum models do not allow any discontinuity, right? So,
Yeah.
but for molecular dynamics, they are based on studying what you call discontinuous systems. There are certain pros and cons for multi-scale, I mean, for continuum approach. In that case, because it cannot yeah, it requires experimental data or some other low scale methods which can be difficult to obtain, and then we cannot look at electronic level of information at the electronic or molecular level of information. Then how they are related is we can either use the results of lower scale to obtain parameters for higher scale. This is known as upscaling, or otherwise we do downscaling, in which we move from higher scale to and let it percolate to lower scale data, lower scale detail, so to speak. Yeah.
Mhm.
And then in quantum mechanics, I mean, at the molecular dynamics approach, we'll have large number of degrees of freedom. So that makes it very tough to do all this multi-scale modeling, right? So that is one thing. And then he moves on to how do we, and what you see here is this is actually this slide is very important one. So we see that at the interface, there may be a mismatch of dynamic properties and other issues. And it also has multiple time scales, because the time scale of an electron is different from a time scale
Good.
of the bulk structure, right?
Fracture, or anything like that. Yeah.
Yeah. So and then and there is also interdisciplinary nature of multi-scale methods like quantum mechanics, then classical particle dynamics and lattice mechanics. Then you have quantum mechanics and quantum chemistry, then thermodynamics and statistical physics. Then atomic scale plasticity, which involves lattice dislocations, and algorithmic issues in large scale coupled simulations. And for collection of data from sensors, we then it's about how to collect data acquisition systems. Then now let's directly go to which are relevant right now, which is introduction to welding processes. So there are different types of welding, say joining,
Yeah.
then
Yeah.
we have mechanical joining, then scale at which we join, micro joining, nano joining, and different states, say liquid state welding, and what do you call this solid state welding and liquid slash solid state welding, in which both exists. So what we need is we need some workpiece and we need some material which has to be melted. So that is essentially the goal in welding, that we have to melt something and which has to be at the interface, right? So that two surfaces can can adjoin. So that is ultimately the physics of welding. So only grain boundaries separate them, but they are there with large force. So so in ideal case to conduct welding, so there are different types of welding, say is fusion welding and then pressure welding, then friction welding. Fusion, they have two types, homogeneous, heterogeneous. Heterogeneous is brazing or soldering.
Okay.
Homogeneous is gas welding,
It's all theory.
electroslag.
Yeah,
Yeah,
we are not interested. We're interested
yeah,
in,
yeah,
yeah,
yeah.
get
But
to
our goal
FEM.
will be just because the modeling has to be, I mean, as per the scope of this course, right? So only fusion
Okay.
welding is what will be discussed,
Okay.
because it's only this model which we can actually because we require some heat source models, and we'll come and we'll encounter in the later lectures. And these fusion welds are created by the collisions of molten base metals mixed with molten filler metals, and metals must be heated to melting point for fusion welds to be produced. And there are also phase transitions which are inherent to the processes. A heat affected zone is created. The cooling of fusion zone is associated distortion, residual stress, and metallurgical changes. Then the principles of solid state welds at temperatures below the melting point are created by either the microscopic or macroscopic coalescence of the material in the solid state, right? And then we come to the enthalpy of melting. So how much we require. So you see there is something known as fusion zone. So in this case, whatever melting takes place, right? So this region is at the highest temperatures. Then we have heat affected zone. It will be the neighboring. Say this is the BM is the base material, or we can also call it as the workpiece. So it's the material onto which the welding is carried out.
Yeah. I, I, you're you lost connection. Hello.
Yeah. Hello.
Yeah. 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 I can hear you now.
Yeah. So yeah, you have fusion welding, then a fusion zone, then you have heat affected zone, and then so it's like how much heat do we require to conduct to melt a given volume of weld. So weld is some material that we are trying to melt, which has to be attached to the other surface, right? So it what is required is first we have to melt the solid, and then after melting, we know that there is also something known as a latent heat of fusion. So it is at this at the melting temperature, we require some additional heat which is meant to change to meant for what you call a phase transition, right? From say solid to liquid phase.
Mm-hmm.
So that's why we see that when you find the total heat required, we have rho Cp Tm minus T naught plus L. So rho is density, Cp is heat capacity, Tm is the heat melting point, and T naught is the initial temperature, and L is the latent heat of fusion. And what are the energy sources for welding? We have electrical sources, chemical sources, optical sources, mechanical sources, and solid state sources. And these are some of the different approaches which we are not looking at today, because yeah, these are some of the details.
Yeah.
Right?
Yeah.
Yeah, now,
Specific to that. Yeah.
yeah. So for us, since we have understood what we are doing, now we'll just go back to the numerical details, isn't it?
Yep.
So
Yep.
now let's just open lecture number 2.
And to be honest, I mean, whoever starts this course, by looking at all the theory, they're like, yeah, I'm not interested in this course anymore.
No,
So the
actually,
main part,
that's very much true. The thing is, as a prerequisite to this course, right? We need to know welding and all. Yeah.
okay,
So
okay. Now
yeah.
I think it is, and also this course maybe just tells you how to model an elastic plastic body, of course, right? Because it's actually elastic body first. Once you melt it, it
Uh-huh.
becomes plastic. So how would you model that plastic in FEM? That's what we are essentially dealing. And also, so when you look at this friction or its welding, it is a
Huh.
heat source. It's a heat source, right?
Right.
And
Exactly. Yeah.
depending on different heat welding processes, the heat source is different. Sometimes the heat source could be point.
Huh, huh, huh,
Okay,
huh.
sometimes it can be volume, matlab, pura volume of surface. So depending on all this, so we want to see, I think FEMA, how would you represent this volume, ka, heat? How would you represent them in FEM? That's what I think we will deal with. But yeah, I want to look at it. True.
Yeah.
Anyways, yeah.
Yeah. Right. Yeah. So this is again just the all these again a theoretical background. So these are like just overview. So it's like the overview of welding is covered in first 2 weeks.
Okay.
It's
Again,
supposed to be
loud.
a complete course, right?
Okay.
So that has been covered in the first 2 weeks. So,
Okay.
but which are not necessary required for the
अच्छा,
I mean for the
इसका
module.
मतलब वेल्डिंग विद एफईएम इज जस्ट 2 वीक्स का कोर्स है, मतलब ही इज टेकिंग एफईएम के लिए ही इज टेकिंग 2 वीक्स, वेल्डिंग के लिए ही इज टेकिंग 2 वीक्स, बस बोथ कॉम्बिनेशन इज टेकिंग 2 वीक्स, मतलब ये वेल्डिंग डू लाइक दिस इन एफईएम, आई थिंक दैट्स व्हाट.
Yeah, actually, that's what it is. You see, right? As per the structure of the course, introduction to welding pro. Then from week 2 onwards, little bit introduction to finite element methods, but it's
Yeah.
always goes into back and forth.
Okay,
So it
finally he's
looks
doing
like
application.
yeah, but there
Yeah.
is no coding part involved as per what we see. So we'll that is what we plan to do here.
Yeah, yeah, yeah.
So now
XFEM
let's
is
come
pretty
to
famous actually. But anyways, yeah, yeah.
which one?
Let's do it.
Yeah.
You have XFEM, you see XFEM, no?
Yeah, extended FEM. So
Uh,
in that case, we
okay.
use some enrichment functions to say extend our what you call basis functions which are meant for approximating something to approximate an unknown. Yeah, right.
Okay. Yeah.
So yeah, so fundamentals of FEM. So FEM is these are like some preliminary details, as in we can do 2D analysis or 3D analysis. So which type of yeah which type
Okay.
of this one we require. So we have triangular element and then tetra. And for 3D elements, we have tetrahedron or brick elements and many other such elements. It depends. Like we learned, right, that we can have numerous number of
Yeah.
types of
Yes.
based on the applications.
Correct.
But however, what things are common are in every such element we have nodes and elements,
Okay.
isn't it? So node is like all these vertices. So it's here where we compute the values of unknowns. And we recall that in certain special types of elements, we need not compute what you call the values at the geometrical vertices. We may even compute the values here, right, at the midpoint of the edges. So I think that we
Yeah.
learned in what are the special elements called CP and
Yeah.
also that's
Yeah.
like
Yeah. 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 Yeah.
yeah. So that
And
is
you
why it
use
is.
these
And then
elements, I think, to deal with different problems you might occur while solving a problem, right? You might have shear
right.
locking, that locking, this
Huh.
locking. So to eliminate that, they use different kind of ultimately function extrapolation. No, say you extrapolate at some point, you
Huh,
create a
huh, huh.
mesh, then they do wahan pe na you do it in middle. So it might give you different value, different approximation. That's something like that's how it
Huh.
is dealt with actually. But
Hmm,
yeah,
hmm,
okay.
hmm, hmm.
Continue.
Right. So finite element method is a numerical tool to solve engineering problems, right? So it's like we our goal is to determine the approximate solution. So discretize on the domain is elements of finite size and nodes. Then we require temperature can vary linearly, quadratic, or cubic within an element, depends on which shape functions do we use to approximate or to approximate the information on. I mean to approximate the variation of the information within an element. Then the basic equilibrium equation has to be satisfied in all the elements, and we know very well that we don't actually satisfy the elements, right? We satisfy in an average sense.
Yep, of course.
Yeah, yeah. Then we assemble all the contribution from all the elements. Now let's come to 2D analysis. So we have such element, and we assume that displacement is assumed to vary linearly within the element. So we have at every node we have u component and v component, which are essentially the x and y components, and then we can express some variation in this form that say u component will be alpha 1 plus alpha 2 x plus alpha 3 y. So these are the variation. This is how the polynomial or the linear function which essentially explains the variation, describes the variation of u within the element, and likewise for v. And our next course of action would be to first compute, although in a symbolic sense, say u1 v1 and u2 v2 at all these three nodes, and then express in terms of say yeah. So it's like we want to compute u1 v1, u2 v2, and etc. at all the other points, and we assume that say we know it, just symbolically speaking. So now you would determine alpha 1, alpha 2, alpha 3. in terms of u1, u1, v2, and that's how the goal is. We'll just have a look here. So the idea is this one. So rewriting expression from equation to say this one, right? So we took the
Okay.
x component and we are able to write in this form. So we know that we know x1, x2, x3, y1, y2, y3 from the geometrical information, and we also say claim to know u1, u2, u3 symbolically. Say we say that okay, we know the values of u1, u2, u3 just
Okay.
in a symbolic sense, right? So then what we are doing is we need to find the coefficients alpha 1, alpha 2, alpha 3, because once we know alpha 1, alpha 2, alpha 3 coefficients, then we are able to determine the variation, right, throughout the domain, isn't it? Say alpha 1,
Yeah.
alpha 2, alpha 3, if we know, then we know the variation of u throughout the domain.
Correct.
So when what we do is we invert this matrix and then express alpha 1, alpha 2 in terms of u1, u2, u3, and with this inverse. So with this, we say that okay, now we are able to we can actually solve for the we can actually describe the variation of the displacement like, throughout the element. And likewise, even for v1, v2, v3, that's how we do. And then what we do is why not determine have a 2 cross 1 vector at every node? Because say at node 1 we'll have u1, v1, node 2, u2, v2, and then node 3, v3, v3, and then denote this by d. So we at for every element we'll have this 6 cross 1 vector, right?
Mm-hmm.
And so where every this element happens to be a 2 cross 1 vectors. So we can just eliminate this vector represented within d for the sake of simplicity, and we are able to have this. Now what we do is now we can express that in terms of u in terms of n1, u1. And now you'll say, but all of a sudden, where has this n1, n2, n3 come into this picture, right? Now let's go back here. Say once we have obtained alpha 1, alpha 2, alpha 3 in terms of u1, u2, u3, we will put it back in this case, right?
Yeah.
So alpha 1 will be expressed in terms of u1, n1, sorry, u1, u2, u3, alpha 2 also in terms of u1, u2, u3, alpha 3. Then what we do is we just club all the terms containing u1 into 1, and then all the terms containing ut, and we'll club in terms of one coefficient multiplied by u2. Similarly for u3 also. So those coefficients of u1, u2, u3, that's what we call it as n1. And likewise for n2 we'll call it u2 will call it n2, and for u3 we'll call it n3. So these are what we call as the shape functions.
Okay.
And yeah, many a time we can predefine what the shape functions are. And yeah, we actually have, I mean, we always define shape functions beforehand. So this is like it has been this what you call concept is explained in a somewhat confusing manner, but that's how it is. We actually prescribe n1, n2, n3 based on the element we have chosen and based on the what you call approximation function that we would want to. Right. So once this is done, then we have this two-dimensional analysis. Then we can write d is equal to uv and then just have a matrix. So it's like uv is equal to 2 cross 6 matrix, and then this displacements will be just 6 cross 1. These are just like we are just expressing this in terms of matrix vector representation, right? Right now we can have this in relation 14 is the important one. So we relate the actual display. I mean, so it's like the approximation of the displacement function in terms of a shape function matrix multiplied by the nodal displacements.
Okay.
Isn't it? So this 14 is what it is. Now what we'll do is, and then the shape functions have some property that it will have 0, 1, the value 1 at for the node at which it's defined. So if it's n1, then it will have value at 1 at node 1, and it will be 0 at all the other nodes. Likewise for n2. So n2 will have a value 1 at node 2 and what you call 0 at all the other nodes. Likewise for n3. So this is the relation of n, what you call the shape function. So this relation is what we call as sorry, this property is what we call as the Kronecker delta property of the shape function, that it will have 1 at the node for which it is defined, and it will have at other nodes it will have a value of 0. So now we construct this strain displacement relation, and as we recall, we have this engineering strain can be defined as gamma X, Y. Gamma X1 essentially tells us the distortion of the element in plane distortion, right? So how much has the angle changed from its initial configuration? So that's what it gives. So the measure of total angle change is given by parcel U by parcel Y plus parcel V by parcel X. Likewise, we'll have for say strain in X direction will be the stretch along X direction, which is parcel U by parcel X, and stretch in Y direction is parcel V by parcel Y. Then we are able to describe in this in terms of some. This representation is known as von Neut representation because strain is also a tensor, isn't it?
Yep.
Yeah, strain is a tensor, so it will actually be 2x2 matrix. Again, from the principle of what you call the minor symmetry, right? That epsilon one ij is the same as epsilon ji. So because of that symmetricity, that 2x1, 2x2 matrix has just three unknowns, which is, isn't it? Because of the symmetricity, right? About the diagonal element.
Yeah. Yeah. Yeah.
So that's why we are able to write it in terms of a matrix form. And then we have all these parcel U or parcel X, parcel V or parcel F, put it all here, and then we can use some functional approach, say parcel U, parcel Y, parcel X, and then have this UV as a displacement, where L is some operator matrix. It's just mathematically speaking, that's how we do. And D is the displacement, what we had seen here. So this is the D, this D. Now what we'll do is we'll substitute 14 here. So then it will be epsilon is equal to L into N into DE, right? L and DE.
Okay.
L
Yeah.
and
Yeah.
DE.
Yeah.
Yeah. So then what we can do is, since we know the expression for N, right?
Okay.
Because N we are prescribing the shape functions we are
Yeah. Yeah.
giving,
It's
right?
given. Yeah.
Yeah. So we can directly apply this linear operator on L on N.
Okay.
Isn't it? We can apply it because N is known. So we can
Yep.
just apply all these linear operators. Then that term is very much widely in finite element literature that has a name, that has a symbol reserved for its own. It is called as B.
Okay.
No matter which quantum FEM book you'll pick up, right? You'll always find B written because it was these notations were introduced by Bathe.
Okay. Wait. Okay.
Yeah, Bathe. Yeah, KJ Beth, right?
I know. It's
KJ Beth.
MIT. No, he has lectures.
Yeah, right. So he's the one who introduced all those notations. Then others also followed, Zenkiewicz and all, Taylor and all these. They kept those conventions. So it's like that's why we recall it as B is what is B is something known as it just relates displacement to strain in linear elasticity. It relates nodal displacements to the strain, right? That's how we say. Yeah, so please, yeah, this 21, right? I mean, if we should just keep this in mind because we use it so many times, right? That this just gets edged in our minds. Okay, that epsilon is equal to BD. So what we see is epsilon happens to be a function. It's related to B. It's related to the nodal displacements via B, and B happens to be a matrix of functions. This is how we have. So it parcel n by parcel n1 by parcel x, then parcel n2 by parcel x, and like this we can have. So this is 3x2 and 2x6, so it becomes 3x6 matrix. And then we go back to elastic strain components. This is what we had learned from Mekshan, right? TSG Mekshan aircraft structures.
Yep.
Yeah, so these are those linear. What we can do is we can sum these these strains to get a net strain. So this epsilon x by E is the actual normal strain. Then the others are due to the contribution because of Poisson's effect, isn't it? So due to sigma y, what will be the extension along epsilon x along x direction? That comes as minus nu sigma y by E. Likewise for minus nu sigma z by E. So that we can we do something known as a additive. This is just as a additive strains. So that's how. So we are able to do this only for linear elastic cases. We cannot actually sum all these strains to get this epsilon x. And we also assume that there is and in this what you call in the simplest linear elastic model, right? In we linearly elastic isotropic homogeneous medium, right? We require
Yeah.
just two coefficients, E and nu.
Yep.
And then because in that what we assume is the shear stress does not affect the longitudinal strain, and longitudinal stress does not affect the shear strain. So that is where there is some
मतलब
some agreement going between these. There is an agreement between the stresses that shear stress won't affect normal strains, and normal stress won't affect the shear strains. So once we do all that, then we have plane stress problems. We do all this, then plane strain problems, and then we come to the potential energy. That the principle of potential energy says that of all possible displacement configurations, a body can assume which satisfy compatibility and constraints or kinematic boundary conditions. The configuration satisfying equilibrium makes the potential energy assume a minimum value. So it's like a body will assume a particular configurations, will assume that particular configuration which happens to make the potential energy the minimum, and it and while at the same time satisfying the equilibrium equations and the compatibility equations and all the boundary conditions. So that is what this principle of so the reason is then potential, I mean, minimization of potential energy gives us the equilibrium equations. So then we use these variational calculus principles to get the actual what you call minimized. Sorry, that then it gives us the equilibrium equations, and we can express the total potential energy of an elastic body in terms of the sum of strain energy and work potential of the applied loads. Right, and for epsilon for potential energy we require all this. We add the contribution due to various strain stress what you call combinations, and then we write the what you call the variations of work done by the loads and potential of the applied loads can be related as this. And the principle follows the concept of minimizing the potential energy of the system, which is 25. Then we have this stress strain relation, right, between all these.
Mm-hmm.
Yeah, and then we come to yeah, then we have what do you call, and here this what we see is sigma is equal to d into epsilon minus epsilon naught plus sigma naught. So this is a very general expression for sigma for linear elastic case, in the sense
Yeah.
that we are also taking into account the residual stress.
Initial.
Yeah,
Mm.
that's what is initial stress equal it's mentioned here, and then we also take into account the initial strain in the body.
Okay.
So this is the most general one in for linear elastic case. When we have stress strain relationship, then potential energy, we do all this. We went systematically that day. So what I wrote, right, we derived for an uniform
Yep.
bar example.
Yep. Yep.
So
Yep.
I used one example to do so that otherwise we don't have to go through all that, right?
Yeah.
That is easy to understand using one problem, and then once you make it abstract, then that is how it will look like.
Okay.
So ultimately we get this equation here after contribution from all the elements k delta minus f epsilon naught, which is forcing function due to initial strain, then forcing function due to external what do you call traction forces, and then T is the traction forces, and P is what is due to let's see what is P for. Okay, it's due to distributed load, and then what is there is W is for, I think, the body weight, body force. Where is it? Let's just where is W? Yeah, it's due to body weight. Yeah, it's due to body weight, and then T is because of the external concentrated load vector. So this is the most general expression for linear elastic case. So we have to solve for delta here. Delta is the vector containing the displacements, and these are all our vectors. So it becomes of Ax is equal to B form. We can take all these to the right, right? Then it becomes Ax is equal to B form, right? Yeah. Okay, now let's go to this
No,
week
we'll
three.
stop here. We will stop here. What do
No,
you
the
say?
thing is, these are just week three. Week three is just about three-dimensional
3D.
elements, right?
Yeah. Okay.
Tetrahedron element,
Just the same
tetrahedron
thing, but
element.
with extended. Yeah.
Yeah,
So
just for 3D. So it goes shape functions. It's the same idea again. We are just extending
yeah,
into
same
3D. Before it
epsilon,
was,
same
yeah,
stress
before it was,
relationships.
yeah, 3x1. Now it is 6x1. Same procedure, and then we are done with 3.
Oh, okay.
Now,
That's interesting.
so yeah, we are just I mean, trying to because we want to discuss about heat source models, right, today.
Okay.
So we'll because that's what will be relevant throughout the lecture series after that. So then I had also talked about weighted residual method that day using a much, I think maybe a more simpler way, right? I think we had talked about this. So weighted residual is we just weight all the residuals and then such that the integration becomes 0. So the
Okay.
same statement has been said in a much complex manner. So yeah. And in residual metal happens to be for our knowledge, right? It depends on based on the selection of weighted function, the residual can be divided into 5 categories. See, collocation method in which the weighting function is chosen from the family of Dirac delta functions in the domain. Then we have subdomain method, which is modification of the collocation method. Then we have least squares method, where the summation of all the squared in residuals is minimized. Then we have the widely used Galerkin approach, Galerkin method. Then we have method of moments. The weight functions are chosen from the family of polynomials. So in this case, yeah, so it's like our shape functions will be different than the weight functions. So in Galerkin method, the same functions are used for testing, which are also the shape functions.
Yeah, yeah, yeah.
So that is the crux of Galerkin method. So that is what it makes it much more what do you call alluring to be used for any practical problem, right? So that is what it is, weighted residual, the Galerkin method. Then the instructor then talked about solving the steady state heat equation problem. The thing is, we'll go through it because this will be used for heat modeling later. So it's
Okay.
like we have this Laplacian of, sorry, kappa into Laplacian of T plus Q dot is equal to 0, right?
Yeah.
So Q dot here is the rate of heat generation in unit volume.
Yep. Heat influx. Yeah.
Yeah, yes. So this is the rate of heat, and then this is the I mean how it diffused throughout the medium. So that is like, so a better way is to put is Q dot is equal to minus K into Laplacian of T. Then it means that okay, whatever heat input is there, that is equal to the distribution of the heat throughout the body. Because ultimately
Okay.
this diffuses through the body, and then our unknown becomes T, which is the temperature. And we have certain boundary conditions to close the problem, that we have this kappa partial T by partial N, which is just the normal heat flux. Then alpha T, if there is some say heat dependent term, and Q is the what do you call heat flow at the surface. And so this is the what you call the generic what you call form for the boundary condition. Then we have heat conduction analysis. So in this case, we do all that. We multiply it with a weight function and then what do you call then integrate over the domain. So that is what it is. That's what we had done for even bar case, right? We took the equation, multiplied it by some test function, and then integrated, isn't it? And then what we got some such expression. So that is what it is. And then we have it's just explaining the same thing, but yeah. Then we have this equation here, equation 12. So this is like the this is like the stiffness matrix, and then this is like the displacement vector, right?
And
And then
it's just how like we have done elasticity. He's doing the same for Poisson equation, right? We
exactly,
all
yeah, yeah.
FEM for this. I mean, this kind of parabolic. I don't know what kind of equation this is.
Ha, ha, ha. So that is what we end with this week 3. And like week 3, I mean the week 3, the third slide may not be relevant right now. If it requires, we'll go back to it. So just to keep our flow, right? And equation number, sorry, week 4, what is discussed is the fluid flow relations. So that is like the continuity equation, then the momentum equation. These are the Navier-Stokes equations, right? And then the momentum conservation equation. Then we also derive the energy equation, which is in equation 13 here. Then we have energy, so the derivation part is given. So the ultimately we have, yeah. So this is the viscous flow for Navier-Stokes equation, which is equation 21. And the natural coordinate system. These are just like I had defined, right? That we define something known as a parent element, and then there is a physical element. Recall, right? We took one by unit -1 to 1, right? One small
Yeah.
element. So that is what it is. So that is like nets. So that is the parametric element, and we want to map from that parametric element to the physical element. So that is given here, but in a much more what you call convoluted manner. That's what is presented. And we have all this for 3D. So it's just like we are just multiplying, say, all those. So if you want to have, say, the first shape function for 3D, then what we'll do is we will multiply three shape functions for the 1D case. So it's like we compose the shape function using direction along x direction, along y direction, along z direction. Then we just multiply all of them, and then we'll see that at the node point at which is defined, it's like 1 into 1 into 1. It becomes 1, and at other nodes it will always be 0. So
Okay.
this is how we define it. It's like we still follow the same thing, we just multiply it. So if it's 2D problem, we are multiplying shape function from, say, along x direction and multiplying with y direction, and then say it will be half and half. So half into half is 1/4. So that is essentially this is how it is. Now, how do we solve it using typical commercial software? We pre-process, which means we build a FE model, then we use computer to process or conduct numerical analysis, and then post-process to see the results. This, which I'm sure we are aware of this. And then we have this, how do we do it? The steps of finite element methods. We first have to discretize the domain, then derive the element equations, then impose the boundary conditions, then we form an assembly equation, and then solve for displacements or whatever is unknown, and then we post process the results. So ultimately, that's how it is. For XFEM, it was introduced that we need to sometimes track in problems where there are moving boundaries and interfaces. We need to track those boundaries. So then we have to go for either interface capturing or interface tracking methods. So interface tracking, what happens is we require meshes that track the interfaces and are updated as the flow evolves. So we track the position of the mesh nodes in a Lagrangian fashion. So it's like the mesh itself moves. In position of the boundary condition at the interface is easy as the nodes lie on the boundary. So this is interface tracking, because our mesh, we allow the mesh to move also. And there is another approach what we have is interface capturing technique. So in this case, the computations are based on fixed spatial domains, where interface function marking the location of the interface is computed to capture the interface. So it's like we just capture it.
It will 0, 1. Yeah, it will do 0, 1, and yeah,
Exactly, yeah.
probably.
And it uses Eulerian description, so there is no mesh deformation. So if there is two fluid flows, we just need some identifier for which fluid is where. So and then we define the interface implicitly on a fixed mesh. In an extended FEM model, what we do is it is known as it's based on generalized finite element method, and also the partition of unity method. It's powerful for discontinuous problems in mechanics such as crack growth, complex fluid interface, and so on. And it's independent of the internal geometry and physical interfaces, such that the meshing and remeshing difficulties in discontinuous problems can be overcome. The discontinuous field is entirely independent of mesh. And we reuse enriched elements with additional degrees of freedom at crack surface and crack tips. Not only it not only simulate cracks, but also heterogeneous materials with voids and inclusions. Right? And yeah, this is like in general, we express some unknown in terms of shape functions and some nodal parameters, right? But what we do is and US and then the p represent number of nodes. But in extended finite element method, we actually add some in some additional what do you call some additional shape functions we require. Not it. I mean, this is not very well written here, so we may have to consider some other resource, but that's how it is. So you see here, right? We are using some enriching functions. So far we are dealing till here, but we actually do use some additional enriching functions to increase the order of completeness, and AK is the additional degrees of freedom associated with the enriched solution, because then we have increased the number of variables, right? Before only
Yeah.
based on our nodes we are doing, but now we have included. So this we need to use some other resource. This is not a very good resource, so to speak. It's not very well presented. Then we come to heat source model. So here is where we start. So we'll just look at the mathematical description. So so the idealized form, right, is this way, that we have some heat source and then we have this melt pool. So we want to model how does this melt pool expand. And we use different, because this is what ultimately provides the heat to the adjoining areas. Then we have this heat affected zone, and the surrounding area will be the solidified zone. And then if we could have differential thermal, so it's like we receive heat flux from heat source, that is this is the heat source, and then we have localized melting and solidification, and then there is also flow of molten material. Right, and then what happens is there will be differential thermal expansion and contraction, which will lead to distortion and residual stress. This always happens, right? If there is thermal involved and then some part will cool, then it will create in residual stress or residual strain also, isn't it, in the body, which are not good. So which are not for what you call these are not desirable things. We should not have any residual stress or residual strain, because otherwise the material will the structure will try to somehow to get rid of it. Say under some intense right, some intense this one, it will be under some intense loading, it may just try to reorganize, so it could just fail and all, right? So that's why we always like structure with no such residual stress or strain. We want to remove it. Residual strain is fine, but residual stress leads to problem, because the body will try to get away, to do away with that stress, right? Hello?
Is it your?
Residual stress.
Okay.
So one example is, say when you cut an onion.
Okay.
You cut an onion into, say, like in some, you want to just cut it such that you want to make some circular discs out of it. So you say you are cutting it laterally, so you get
Okay.
plates after plates, right? Now if you
Yep.
you just take one ring of the onion, say from
Okay.
there, one ring, and in the moment if you cut it, right, the ring will just open.
Yeah.
Isn't it?
Yep.
So that is because of what you call. Maybe I'll just show you something. Yeah, term paper. I think that is the best way.
Well,
I had
okay.
this was a part of my some biomechanics course during lockdown. Is it opening? Okay, there's the one. Okay, there's a term paper I see. Okay, let me open onion ring. The onion ring experiment report. So see, so it's like, see, I had I'll just open one page. So onion ring analysis experiment. So the goal was to
Oh, that's
cut
nice.
that, cut that and then fit some constitutive model into that. So it involved all the process, doing experiment, measuring it, doing image processing, then fitting into some constitutive model just to see how the stress will look like, stress variation. So say I have these initial onion rings before being cut, right?
Mm-hmm.
Now, when I cut it at one location in the cases, you will find that some of them will go inside and the outer ones will come out. So it is like the inner one were in compressive stress, and as we moved outwards, they became under tensile stress. See, right? When you cut it, how it just so this is like the residual stress-free configuration for each of the cases. Because if it were stress-free, right? So only this part, this ring was stress free, even when they were it was a part of the onion.
Okay.
But for others, you see that this one, a segment went inside. In others, they just separated, isn't it? So this is like the stress free configuration.
Yeah.
So it's like it's the residual stress which actually keeps them intact. The moment we
Mm.
allow it to go free, right, they will take up different orientation, different configurations. So this is how I did. Yeah, we use some ImageJ software which is developed by some NIH lab in US. Then I did all this tracing, then measured it. So measured all this here, then tried to use some funcs model. Funcs model is a very nonlinear model to model stress and strain. So this is the funcs model as per funcs model, right? So I just feed the data, got, so this is the then used in incompressible new Hookean strain function, put it here, got all these, expanded all these, and then tried to fit, yeah, they plotted some graphs using all that data, yeah. And there were some inconsistencies in our in my analysis, so I just put it here. So
Okay.
I saw that in certain disks, what happened is it looks like everyone were under some other different kind of stress. Like in this case, it all happens to be compressive.
Okay.
So yeah, that was essentially the goal. Yeah. So it little coming back here. So that is why the need for a stress this comes into place here. Close this
All
2B.
this one. Yeah.
So now this
Yep.
was the what we are dealing with the fusion welding, right? Then how for heat conduction we use this Fourier's law, and then we use for heat transfer, energy transport, and Navier-Stokes equation we have to solve because ultimately there is also flow going on, flow of the molten material. Then we have keyhole formation when we use laser welding, plasma welding, or electron beam welding. So this is the essentially the schematic. So we apply some pressure, then there will be some evaporation at the surface, free surface. Then convection radiation is through which this heat will particle this be transferred to the ambient atmosphere. Then we have all this solidified zone, liquid pool. Then because of all this buoyancy effects, the colder one will move upwards, hotter will come down, something like that, right? That goes on. This is the melt pool actually. This is the melt pool, and this is the base material, and we are applying heat source from above. So
Okay. He
condition
also
mode
has.
model is, huh?
He also has electromagnetic field. I don't know why he's bringing up about electromagnetic. But anyways, continue.
Yeah. Right, so it's like, yeah, so this is where we come condition when heat source model fails if material contains some free active elements. We consider only heat transfer and fluid flow, momentum transfer due to solid surface tension force, buoyancy force, electromagnetic force. We solve electrical conservation of mass momentum energy equations. Right.
Yep.
So then we have this what you call physical aspects of solid state welding, frictional heat generation, sticking and sliding, plasticization of material, physical, and then heat conduction, material flow, solid state phase
Okay.
transfer, distortion, residual signals. And how can we model it? We can use sequentially coupled or fully coupled thermomechanical analysis, thermal model plus mechanical model, normal
I know.
conduction based model,
Okay.
right? And then we are
Okay.
solving this heat equation. These are the boundary conditions. And then the thing is, since this happens to be very much axisymmetric in nature, right? We just take one plane. So it's like if we revolve this plane about the vertical axis, right? It will just make the entire one pool. It will appear as a this one, right? It will actually give, I mean, or mimic the actual environment. So now the goal is to how to model the volumetric heat source term. So that is where all the modeling takes place. The conduction heat transfer based model cannot undertake greater rate of transfer in the growing weld pool. So inclusion of a term representing volumetric heat source. So our entire focus is on to model this Q dot because this is what is the main thing, right, going on, because this gives us the heat generation term. Then different volumetric heat source models can be used in different welding process. There is a distribution of heat flux, mapping with geometric shape and size of volumetric heat is important. Yeah, so that is what is necessary. And these things, yeah, contain some analytical descriptions, which we'll leave it for today. We'll come for to the actual particular different types of approaches that have been done. Some of them. So say I'll just have 2 pages again. So say we use this circular disc shape heat source. So this is the circular disc shape heat source. Then we have ellipsoidal heat source model is ellipsoidal. It is in 2D. Then we have double ellipsoidal. So double ellipsoidal means we have it looks ellipsoid. So you understand, right? It will be one ellipsoid segment of one ellipsoid here and other ellipsoid here. So that is
Yeah.
what double ellipsoidal. Then we have quadruple, in which case there is some differentiation. So this one will have different A1, B1, and this one will have different A1, B1. Then this one also different, so that we have four. So two different A's we have. So it's like this part will have different A1, B1, and then so it's like we have four different uh, four quarter sections of sorry four sections of four different what should I say? It's a combination of four quadrants of different ellipsoids, ellipses. That's what I mean. So this will be quadrant of one ellipse. This will be quadrant of another ellipse. This one will be the third ellipse and fourth. That's why we call it quadruple ellipsoidal heat source. These are like just modeling, and then it each will have difference. So if it's symmetric, right? In symmetric, what happens is it won't be able to model some shears. It's as if everything is uniformly distributed throughout. Right, so this will, revise it again. So these are just like the different ellipsoidal heat source model, double ellipsoidal. Then in quadruple, you see, right? You see the segment here, A2,
Okay.
A1, then you have B1, B2. So it's like one quadrant of one ellipse, another quadrant of another ellipse,
Yeah.
third ellipse, fourth ellipse. Yeah. This what the advantage is that it can also account for non-symmetric energy distribution for dissimilar materials.
Okay.
And if there is no, and for double ellipsoid, it can only model heat source only. And then for the ellipsoidal one, it only will model only stationary stationary welding process. And then we have adapted heat source model. It depends on the limitations are that it will depend on different heat source parameters. This happens to be more generalized, but it becomes tougher because we require to define many heat source parameters. It requires modeling, lot of mapping between parameters. To be honest, I didn't understand this much. It looks like we may have to refer some books from where the instructor has taught. So it's just like mapping between certain standard configurations. Then laser welding, the maximum intensity distribution. Then we have all that, yeah, how to model a different hourglass heat source. Then we have all this upper truncated. Different heat source for ski hole mode, laser welding, conduction versus ski hole mode. Conduction means low power intensity and low aspect ratio, which means depth versus width, no vaporization. So in conduction mode of laser welding, there won't be any vaporization of material. In keyhole model, there is high power density and very high aspect ratio, and we can also do deep penetration, and then it becomes, so this is like keyhole, right? It's as if we are digging deep into the material. So that is
Yeah.
where the name comes, keyhole mode. Conduction mode only remains at the surface, shallow. It's very shallow in nature. And the advantage of this method is we can do high depth width ratio, low distortion, small heat affected zone. But in this case, there is a large heat affected zone, because of which we can get many unnecessary deformations in the workpiece. The mathematical modeling is we require again geometric keyhole shape and size, then semi-analytical method to estimate keyhole shape and size and then keyhole profile we require, right? And then
Krishna,
all these
actually,
parameters.
we'll stop here now.
Sure,
Is it
sure,
okay?
sure.
I need to take
Yeah,
a call actually, so hopefully.
sure, sure. So it's like, yeah, this is like about the heat source. And then next time what we'll do is we'll just take a look as per what we had planned, right, in this session. So it's just like all that repeated.
How would you
And
do that in
then
FEM? That whole heat sources. Yeah.
yeah, so it's like we will start coding this from next time onwards. We'll try to
Oh, that's great.
implement one thermal energy, and then we'll
Okay.
also try to model some different heat source models.
Okay.
So our yeah, so this is our goal. Yeah, and then we'll also try to learn how to what you call model. Our goal would be to say time dependent problems, right, in Phoenix.
Okay. Keyhole welding. Okay.
If we are able to do some time dependent problems, right, then we can actually understand then how to carry. Then it all become. I mean, then we only need to model the Q dot. So we required to do time dependent problems in Phoenix. Solving PDs. Okay, gallery of finite element. In our this there was in Phoenix resource there was no such mention about this, right? In the resources, did
About.
any about some solving how to solve time dependent problems? No one talked about this, right?
I'm just checking in SPH if, yeah, there is something dealt with it like this. Okay.
Okay, if we just look right, even if we just take a look, that would be wonderful. Just how to we'll see how time dependent problem is solved. That's it. So we can start from there the next in our next meeting, next tutorial sessions. Yeah, this happens to be a complete time independent problems. This is also maybe some steady state problem. I think these are all steady state problems, right? Because we can clearly see there is no time integration going on. Yeah, there is also time independent problem. Time stepping, but it's like solving a quasi-static problem. Okay. I see. So it's like this one has something to do with time dependence. Okay. This tutorial has something. And let's look about what this Blair's has to say. Uh, Actually, the word has JS token because JS token is the most widely used tutorial. Let's see what JS token has to say. Did it solve any time dependent problems? If that is, then it will be really worthwhile for us. What how did he solve heat induction? Okay, here he solves. Okay, here he solves, right? You see. So heat equation. Actually, then he's talking about solving heat equation. You see,
Yeah.
question 17. So we are okay. Let's just go through. I mean, we'll not go through in detail. Let's just see that. Okay, how he has done it. That will be wonderful. So you take some initial condition and then initial configuration, then time dependent output, variational problem and solver, bilinear form assembling, use PSC to solve linear solver because that's also a linear problem. Visualization of time dependent problem using 5 updating the solution right hand side per time step. Okay, that is the goal here. So okay, so that is where we have to focus. Okay, fine. I see. I see, and then we can use. Okay, so this is the tutorial we'll follow, right? So yeah, this is what we'll do.
Sure.
Yes, you see, right? Even what if we can also choose some problem for which we know the analytical solution and then match the results also. So okay, that's fine. Yeah. What is a nonlinear? Then that's another thing. Okay, we can use the ideas from your what if say there is different thermal conductivity. If it not happens to an isotropic material, then how can we do that? Okay, so these two tutorials will help us. So I think that's what we'll go do from the next session. Yeah, since I mean we have been able to complete the scope of this today's tutorial session. So yeah, what we had aimed, right? So what I'll do is maybe I'll stop recording and we'll meet during
Yeah.
the I'll stop
Okay.
sharing first and I'll just stop recording. We'll make next week. Yeah.